Here's an extra. This is not part of the higher course. It will not appear in the higher exam. In fact, it's part of advanced higher maths, and you could do it again in first year university maths. But it's just a little illustration of where this rule comes from. That when we differentiate x to a power and we want to differentiate that, we multiply by the power and take one away to get a new power. Where does it come from? Well, let's have a look at a fairly simple graph for a simple function, f of x equals x squared. A parabola coming like this. And let's say we want a rule to give me the gradient anywhere on this parabola, anywhere on this, what is essentially y equals x squared. Let's think about this point here. If I want the gradient at that point, now the gradient is changing all the way up there, and the gradient at that point at least lies something like that, the same as the gradient of the tangent at that point. Well, let's think about this line here. It's not the same as the gradient of the tangent, but we're going to use it as an approximation to start off with. So if this is my point 1, let's say we create a point 2 here, and let's say that its x-coordinate is 3 more. So my change in x going along the way is going along 3 from this first point. And then I'm going up here. And there's my change in y. So at this point, I'm saying I've got the point x, and the y-coordinate is x squared, because it's a graph of y equals x squared. My second point is 3 further along, so that's x plus 3 along, and going up the way. If it's y equals x squared, it's my x coordinate squared, whatever I start with here. So this point is x plus 3, and my y value in here will be x plus 3 squared, because we say we get the y coordinate by squaring whatever the x coordinate is. Now we know for a straight line, gradient, change in y over change in x. What's my change in y? Second point is a y-coordinate of x plus 3 all squared. So this is x plus 3 squared. Take away the y-coordinate down here. Remember we said this is the point x, and the y-coordinate is just x squared, because that's what the curve is. So y1 is x squared. What's my change in x? Well, we said we're going from here to here. We're going along 3. So I'm just going to write my change in x is 3. Let's work out that gradient. X plus 3 squared means multiply it by itself. Take away y1, which was just x squared, over 3. Oh, okay, so that's x squared plus 6x plus 9. You can work it out yourself if you don't believe me. Take away x squared over 3. And when I tidy that up, x squared, take away x squared, so that goes. Oh, 6x plus 9 over 3. I'll just divide them both by 3 then. That's 2x plus 3. So the gradient of my dotted line here has worked out from change in y over change in x to be 2x plus 3. Now that's not the gradient at the point I want down here. It's the gradient of the dotted line. It's the gradient when I consider going from here to a point with the x 3 further along. As I say, it's not super accurate, but it's better than if I'd said, well, what about when x is 4 further along and I get something up here? But it's not as good as, well, what if it was only x? It was plus 2 further along, or plus 1 further along, or plus a half further along. The closer I bring this point down towards this point, and then do my change in y over change in x, the better my approximation will be to the gradient of the tangent. Why don't I just say, well, let's just do 2 points at the same place and do my change? Oh, because then my change in x would be 0, and I'm never allowed to divide by 0. So we considered what happens when it's 3 further along from my x, and that gave me x plus 3 squared minus x squared. Well, let's just say it wasn't 3. As I say, it could have been 4, could have been 10, could have been 2, could have been a half, could have been a quarter. Well, let's just say, let's consider the general form. What if I was not 3 units further along, but I was h units further along? So my first point here is x, and my second point up here, the x coordinate is x plus h, the first x coordinate plus h further along. What happens to my formula then? Well, instead of x plus 3, it's x plus h squared. My change in x just becomes h. X plus h times x plus h over h. What's happened there? Well, if you work out x plus h times x plus h, you get x squared plus 2hx plus h squared, all divided by h. The x squared still take away. Divide by h, we get 2x, and h squared divide by h plus h. What happens as on here, h gets smaller and smaller, because we said as this point moves down the curve closer and closer to the first point, my gradient gets more and more accurate. So we want this distance between these 2 points to be as small as possible. That means let's make h as small as possible. And we say that means this equals, and we write it as the limit as h tends to 0. H can never be 0, because at this point we divided everything by h, and we're not allowed to divide by 0. But we can say as h gets closer and closer to 0, so this stands for the limit as h tends to 0 equals 2x, because this bit here gets so close to 0 it makes no odds. But what was I doing there? I was working out the gradient as my change in y over change in x for the graph f of x equals x squared. So what in fact we're really doing, if we're differentiating x squared, is we're saying that's f dashed x, for x squared is 2x. And in the same way, we did this example for f of x equals x squared, but we could have done it for x cubed, right? Or indeed generally for x to the power of n. And you can even do it for negative powers of x, right? Or even there's a formula for sine x or for cos x, and you could do this exact method. Say, well, what happens if I went a little bit further along for my change in x? And what happens if my x coordinate to get my second y, well, that'll be the same as x plus h, and whatever happens, squared or cubed or 1 over or 1 over this squared, all right, or even sine bracket x plus h, take away sine, and this works out each time. And there's a formula we will meet later on for differentiating sine and differentiating cosine. But that's where it comes from.